Please welcome to the stage Director of Exploration Technology at NASA Ames Research Center, Rupak Biswas.
Welcome, everyone, to the invited talk session on non-traditional applications of HPC. Our first speaker this morning is Dr. Jana Thayer from the SLAC National Accelerator Laboratory. She's the Division Director for the Linac Coherent Light Source Data Systems at SLAC and is responsible for data acquisition, data management, and data analysis for the LCLS facility and development of the next generation of data systems to support the LCLS-II upgrade. She's also the PI for intelligent learning for light source and neutron source user measurements, including navigation and experiment steering project, which facilitates rapid data analysis and autonomous experiment steering capabilities to support cutting-edge research that tightly couples high-throughput experiments, advanced computing architectures, and novel AI/ML algorithms to significantly reduce the time to science at the light and neutron sources. Jana started at SLAC in 2004, working on the Fermi Gamma Ray Space Telescope and leading the Large Area Telescope flight software team from 2006 to 2009. Jana has a PhD in elementary particle physics from The Ohio State University and has long nurtured an interest in data acquisition systems and high-performance software in the fields of high-energy physics, astrophysics, and photon science. The title of our talk this morning is How I Learned to Stop Worrying and Love the Data Deluge. Dr. Jana Thayer.
All right, good morning, everybody. So my name is Jana Thayer, and I run the data system at the Linac Coherent Light Source. And I'm here to tell you today about some unconventional uses of HPC, specifically the way that the Department of Energy user facilities, experimental facilities, use HPC to further their science, do science discovery, and accelerate the future promise of science. So I'm going to tell you first about the challenges of these experimental facilities and why it is that we need HPC in the first place to analyze some of this data, and why using HPC is such a challenge. So for starters, the Department of Energy user facilities are a many-splendored thing. There are many of them. I show a couple of pictures here. They are diverse engines of scientific and engineering discovery, and the things that they all have in common, so they're wildly different. This includes the atmospheric research monitoring. It includes the light sources, which are better than flashlights, I promise you. I'll tell you what a light source is. It includes accelerators, tokamaks, Joint Genome Institute, and the Environmental Molecular Sciences Lab. So this is a breadth of science that these facilities are doing. And they are complex systems. The thing they have in common is that they all generate data, and we are all trying to control these instruments using the data that's coming off of it in real time. These are built at sites that are often 60 or longer years old, so they're decade-old facilities that have been upgraded many times. Once the facility is upgraded, it can do science for another few decades before its next upgrade and its next upgrade. So it's a continually changing world, but its foundation is in decades-old technology. So we are building these modern systems on top of old infrastructure to do modern, cutting-edge science. The other important thing to note is the word user in user facilities. So users are the people who are the science researchers that want to do the science. They want to answer the science questions. Note, they are not computer science researchers. So these people are using these facilities, these complex instruments, to answer complex questions. And so why is it that we need to use computing to do this? So the problem space, I'm one behind. Look at that. OK. So I'm going to move on here. All right, so the problem space, I'm going to focus in now on the light sources. So the light sources there are 5 Department of Energy light sources in the US. And over the next decade, they are going to generate about an exabyte of data and require somewhere between tens of petaflops to an exaflop to analyze that data. And it's always good to have an analogy. And so the analogy we use is that this exabyte per year is something like 1.5 million Netflix movies per day. Only we're not watching these Netflix movies like a human being sits in front of a TV and watches. We have to analyze every frame of these movies within the context in which that frame was taken, and we have to put it together in relation to the other frames around it, and we have to understand the whole picture of what that movie is telling us based on these individual frames that have to be analyzed. And it gets worse because we have hundreds of experiments per year at different beamlines. They change every week. So it's a very challenging problem, and many of these instruments require the use of an exascale computer in order to do that analysis. So it's quite a challenging problem to provide the infrastructure that's needed in order to solve this particular problem and answer the science questions that are being asked. So now I will focus in on the Linac Coherent Light Source, which is the light source that I work at. This is a picture of the SLAC site. This is SLAC with a C, not with a K, just to make that specification. And the linear accelerator is the 2-mile-long building that you can see stretching out behind me. If you were to land at San Francisco National Airport, and you look out of your left window, first you'll see Apple's headquarters, the little UFO, and then you'll see Hoover Tower at Stanford. And then if you look, you will see this 2-mile-long building stretching west into the sunset. That is our linear accelerator. It generates our X-rays for us that we then use to do science. Down below, in the sort of center to the right of the screen, there's a little donut, and that is SSRL, that is a synchrotron. Those tend to be round. And it is also one of the light sources that we have that's been operating at SLAC for a very long time. So a little bit about LCLS. So if you look at the view from the sky, so I should say what LCLS does. This is what a light source is. We generate X-rays, and we use those X-rays to image things at the atomic and molecular level with femtosecond precision. So what that means is that we can put a material, a chemical, a biological component into our beam of X-rays and use those X-rays to tell us what atoms are present, where they are relative to each other, and how they move with respect to each other as a function of time. And this can teach us all sorts of things about photosynthesis, about biology, about how things bind to a COVID crown, and everything from material science to plasma physics. So we cover the wide range of things there. Now, if we look at what's happening and how we generate those X-rays, the LCLS is unique and interesting. It is an X-ray free electron laser. And most of that 2-mile-long building is actually underground. It's an underground lair. And we generate electrons at the one end, at the west end, and we speed them up to 99.99% the speed of light. And then when they get to the end, we generate X-rays. How do we do that? We wiggle them back and forth. That's the technical term. We wiggle them back and forth, and that wiggling produces concentrated, very bright pulse of X-rays, which then go down the beam line to the experiment hall. The electrons get dumped for science, and then those photons proceed down into the experiment halls, one of 10, that will allow this X-ray to hit a sample. Those X-rays diffract, they scatter off that sample, and they hit an X-ray detector, a high-speed X-ray detector. My system, and you'll notice in that picture, that's my system. What's happening right now is all the data system. We capture those images, we save them, and then we analyze them, we reconstruct what's happening, we take little dots on a screen, and we transform them into the science, which is where are those atoms, how are they positioned relative to each other, and how are they moving with respect to each other as a function of time. One thing I should have noted is that we are often controlling what that experiment is doing. If you need a laser to excite something to to take an electron and bump it to a new level, if you need something to catalyze a chemical reaction, These are all things that are controlled as part of that experiment. So it's worthwhile to look at what one of these experiments looks like. So this is one of the instruments that we have at LCLS. There are 9 other critters like it. If it reminds you of an underground lair or evil mad scientist sort of device, you're probably right. It's probably all of those things. But one thing I want you to note is how many wires are coming off of that. So the wires are all either data or points of control for this instrument. So it's also interesting to look at this in contrast with the previous talk that showed the Google data center and had all of these lovely, well-dressed cables. You look at this, and right there, you know there are scientists doing this, right? So it's lovely, and it's a beautiful thing. And the other thing that's remarkable about this is it's actually a Lego. These pieces of instrumentation can come in and out. We can use different detectors every week. We can put in different sample injection facilities. We can use different lasers from week to week to week. Each instrument has its own particular reason for being and does have some standard features that it offers, but fundamentally it's a changeable beast. Every week it's different. It's put together in a slightly different way. It has to be controlled in a different way to answer a very different question that the scientist is asking. The other thing to note is that currently we're in the middle of an upgrade. We are taking this accelerator that's generating these X-ray pulses from 120 times per second to 1,000,000. So that's a factor of 10,000. That is a huge increase in data rate that we're expecting to see. We're on that ramp right now, and we just see the data rate going up. So this is a step function in both our data needs and our compute needs. So our raw data rates currently are in the 200 gigabyte per second range. In a couple of years, we're going to be exceeding a terabit per second coming out of the detector. Somehow we have to take that and do something with it. Recorded data volumes, because we have a capable data reduction pipeline that reduces the data on the fly before it hits disk. Our recorded data volumes are of order petabyte per 12-hour shift. So that's the good news, is that we're doing some data reduction very close to the detector. But it still amounts to about 100 petabyte per year aggregated. And across the DOE complex, there are other instruments doing the same thing. So it's a lot of data. So to illustrate a little bit what the breadth of things is, you can see these are a few hand-picked different experiments that we do that show the data that you expect to see that comes out of it. You can see that the data for these different types of experiment technique are wildly different from each other. So when you're doing an analysis, it has to be targeted to the experiment technique. And we get hundreds of experiments per year, but roughly 20 experiment techniques, 20 different workflows, but all with extreme throughput and compute needs. So how extreme is that compute need? At the LCLS-II challenge at 1 megahertz and why we need high-performance computing, what we've done is we've kind of analyzed in aggregate the experiments that we expect to be able to do over the next few years at this megahertz rate, and we've created a plot that says and we've benchmarked those workflows to see how much compute do we need, and we find that many of them sort of go into that lower part of the bin. That bubble represents the percentage of experiments that require a certain amount of computing. So down towards the bottom is the petaflop range, and up towards the top is the exaflop range. And on that bottom, you see like 80% of experiments really require only, within a petaflop of computing. That's not so bad. But then up at the top, that's exascale computing. We don't have an exascale computer on site. We have a mid-scale, we have an OK computer. We have a mid-scale compute facility. That's the SLAC Shared Science Data Facility. And it is very capable of handling that 80% of experiments that fall into that petaflop-ish to 5 petaflop-ish range. But anything beyond that, we cannot do, because we cannot produce an answer within enough time to control the experiment. So the question is, do we not do those experiments? That's photosynthesis, though. That's coronavirus. These are important to us. These are vital questions that we need answered. So rather than give up, we work smarter. We surge those experiments, we stream them to a leadership class facility such as NERSC, and we analyze the data there. What makes it challenging is the timescales involved. These are all time-sensitive analyses. So this is what this looks like from the user's point of view. So again, I said there are researchers that are coming in, anywhere from groups of a handful to 100 people will come in to do an experiment. The procedure starts months before. You start with a proposal. This gets ranked by an independent committee that says these are the highest profile experiments. These are the ones you should do. Then these experiments are allocated beam time. Then it gets passed to the facility. And the facility does the experiment planning. We work with the scientists to make sure that they get the right detectors, they get the right sample delivery, they have the right support, and also the resource allocation. Do they get what kind of computing do they need, how much, what kind of real-time needs do they have, and so on. Once the beam time begins, they get 5 days. 5 days to take their data, to get their 5 petabytes of data. 12-hour shifts, day shift, night shift, so they're on days or they're on nights. And they begin this loop where they start taking data, and there's currently a lot of hand tuning that still happens, where you have to align the beam, you have to get it to hit your sample, you have to figure out where your detector should be, you have all these points of control that move things and change things. Experiments are living, breathing things. Even the sun shining on the side of the building will make the building expand, and that will affect what's happening in the science, on the images that you see. You have to be able to adapt to that, or else you can't do your experiment. And so there are both fast and slow cycles of experiment control. So you take the data, you do feature extraction on it, produce actionable information, use that to control the experiment. You can do that on sort of the second to sub-second level. And then there are things like fast feedback that are looking at data quality monitoring that can happen within minutes. There are things that let you decide, what should I do next? Is my beamline appropriately aligned? Am I getting enough hits? Am I seeing the right signal to noise and things like that? And then there are things that take hours to decide. You have to accumulate enough data to know that you can, in fact, reconstruct a structure. And so these autonomous feedback loops are using all of the computing we have locally and sometimes even remotely in order to make these decisions. So the on-shift analysis begins immediately. It gets processed, and within a minute of ending an acquisition cycle, these usually take about 10 minutes, within a minute you get a response that says, here's what we saw, here's the analysis. Off-shift, people are often running analyses, multiple analyses at once, 10 passes through all of the data they've taken during the day and previously to make a decision about the next day. After the experiment, for about anywhere from 4 months to a year, people are analyzing the data, they're producing publications. That data sits on our systems, it's archived for 10 years, and we have seen publications. We do still have 14-year-old data, and people are still making publications off of it, so they are still going back to that old data and gaining more insight using newer techniques. So this is why we need an edge to HPC interconnected system in order to drive these experiments, to get the data we want, only the data we want, and to make sure that we can provide a response, provide an answer to the science question while the scientists are still there, still paying attention, still working the experiment. So how are we leveraging these Department of Energy leadership class facilities to do this, to solve these problems? So the problem that started it all, there we go, is the single particle imaging high rate analysis problem. So this is a very typical example where we have a jet of particles that are injected into the X-ray beam. The X-ray beam hits that, the light scatters, it strikes a detector. My system then captures that data, records it, and we have this data reduction. So every once in a while, the X-ray beam might miss its target and you see nothing. For those cases, we just throw it out. There's no information to be had there. Don't bother to keep that. And then after that, it gets transferred to the offline system and the analysis is reconstructed, but this requires an exascale. So somehow we had to make a connection from SLAC to a high performance compute facility. We had to go outside of SLAC to get enough computing to be able to keep up with the analysis at the rate at which data are coming through, to do the reconstruction, to say, here is what's happening, this is what we think we see, here's where the various atoms are. And so the XFL project was born. XFL is Data Analytics for Free Electron Lasers. It is an ECP project, and it made that linkage between SLAC and NERSC possible. And it was working smarter on at least 3 levels. There were algorithmic improvements, sort of making the algorithm itself smarter and more efficient and better able to mine the data that's there. Building a framework at LCLS, not just for the one experiment, but for all experiments that allows you to take the data and scale to hundreds of thousands of cores to do the analysis without the user having to know anything about how to do that. And then the infrastructure to move data out to NERSC, get it into the computer and over ESNet, and get it to run so efficiently. And again, the users themselves are scientists. They do not have to worry. They do not want to worry about data movement, how to scale things so that it can run as effectively on one computer as 100,000. So this was a several-year project, and not to belabor the point, it was successful. We now have a SPINFL code that can reconstruct the structure, even if that sample contains a mixture of conformations. And even more importantly for me is that we have an implementation of the Superfacility API implemented at SLAC that can now be used by any user at SLAC. And that means that we automatically can click a button and stream. It's not quite that simple, but click a button, send data out to NERSC, have things analyzed there at larger scale, and then bring the results back to SLAC so the user can interact with them. So this is what that pipeline looks like in action. This is on a 120 hertz style data set, so a smaller style data set than the megahertz one we're anticipating. But the upshot is that we transfer data, we use ESNet, gets to NERSC, it has to get into the computer, and sometimes that last mile problem is quite difficult to solve. The limitations are purely, technical in that you need to get you have the speed of light to contend with, you have to have your data travel some number of kilometers to your remote data center, it has to get into the computer, and then it has to operate on, the computer has to operate on it, and then send the results back. So the other thing that you run into are policy questions. So as soon as I leave my site, there's a little bit of complexity involved with added impedance in trying to figure out how to work with somebody else's security, how to get accounts, little things like that. So these are the things that make it quite difficult to do automated real-time analysis, but we've tried to hide all of those details from the user as much as possible. And the upshot is that at this point, we expect to be able to get analysis results within minutes at this high rate. So where do we go from here? So LCLS and SLAC have extreme computing needs that require the use of HPC compute. There are experiments that we would not do, could not do, if we did not have access to a NERSC-like entity out there. Turns out, real-time analytics is not our only use case. Between the time that XFL started and now, ML and AI have burst on the scene. And our users have virtually unbounded aspirations for doing AI, everywhere from controlling the experiments to doing the analysis and reconstructing the science. The technology there is evolving quite rapidly, more rapidly than facilities are designed to evolve. There are algorithmic improvements, improvements in AI/ML, and new hardware that are coming out all of the time. The DOE, the Department of Energy, is investing in this infrastructure and programs to accelerate scientific discovery. So you may have heard of the High Performance Data Facility, the Integrated Research Infrastructure, and the AI for Science, Security, and Technology initiatives that are trying to put these pieces together and form a coherent, integrated environment for these experimental and observational facilities that have these time-sensitive, intensive compute needs to use these resources that are in the DOE. So the LCLS-NERSC partnership is a seed, it's a model for going forward, and how to connect local and remote HPC resources to do science. So what's next for LCLS? When I look in my crystal ball, how are we going to need to expand? What are we going to need to do at these facilities? Is it just real-time analytics or what? So looking ahead, what I see is that we will do as much processing locally at SLAC as we can, because it just makes sense from the perspective of experiment control. Our experiments are there, we know how to run them, we know what needs to happen, we know when to pulse a laser, we know how to control that dance of making the experiment do what it needs to do in order to produce the science that we want to investigate. And the SLAC Shared Science Data Facility, our mid-scale facility, is the landing pad for our data set, our very large data set. It's also the landing pad for the Rubin Observatory and for SSRL and for other instruments at SLAC. We have a gateway from there to ESNet to use the DOE OSCAR facilities. And those OSCAR facilities will be used for everything from that real-time analytics, which we need, to multimodal analysis, where we're incorporating data from other light sources or simulations, to do model training, large-scale model training, to do the inference that's needed to run these experiments, and rapid model retraining. As I said before, these experiments are living, breathing, dynamic things. They need to change as a function of time, sometimes on an hourly basis. A model that you've trained on old data may not be perfectly suitable. You may have to tune it, which means you have to bring in the infrastructure needed to do that rapid model retraining. So what's next? So we're trying to produce actionable information. So this is what we need in order to do those tight, small feedback loops. And so in order to respond to things every microsecond, which is, we are in this mode where we have data coming in every microsecond, and we want to be able to react to it on something of order a second or less. And so we're trying to do AI-enabled classification or feature extraction at the extreme edge. So move that as close as necessary to the instrument to produce actionable information that you can then use to control what's happening in the experiment. So we've successfully taken a model that starts out as fairly large, and fairly large, several hundreds of millions of parameters, and squeezed it down to fit into the relatively small, compact space provided by an FPGA, which is order 10,000 parameters. So, and likewise, we've taken another model that we've trained on lots and lots and lots of data and tuned it to very specific experiment use cases to do peak finding at the edge. So this is looking for those little dots of light in the images. And so that's one way we're going to use things is to do, we'll do the training, we'll do the stuff at the edge part, but HPC is needed to do that training, and the knowledge transfer, the knowledge distillation to get to the large model and the small model to behave the same way so that we can run it at the edge. There is a 5 light source and neutron source effort in order to improve the infrastructure for experiment steering. So it's trying to close the loop between fast analysis, machine-assisted decision-making, and the DAC. So here, the light sources and neutron sources would like to sort of interact with their experiments in similar ways. This is based on the Blue Sky framework out of LCLS-II, out of Brookhaven National Lab. And it should present a uniform interface so that when we want to go out and interact with the high-performance compute facilities, we'll at least have some uniform way of requesting the resources we need and getting results back and moving the data along and things like that. One illustration of this machine learning using machine learning-enabled real-time experiment steering. It helps users make physics-informed decisions. And just to point out what elements are involved here, you have to develop a data-driven experiment steering framework. You want to suggest the next measurement. Tell me at which time point I'm going to pulse the system with a laser, and then I'm going to see what's happening with that system as it evolves through time. I'm going to investigate, this much time after, and this much time after, and this much time after. But the thing is that if you look at some of those plots down at the bottom that show these little pulses, the peaks and the valleys are what's interesting, but if you're just sampling randomly, you might get something in between. So you might see a straight line when what really is happening is something like that. And so you need a surrogate model that will tell you what the physics is that defines that, and then incorporates that, combines that with what's happening in the experiment, which needs to be analyzed first, and then compare them, and then feed that to some Bayesian optimization engine that can then decide, here's what you're going to do next. Here's the time point that's going to give you the most information. All of this requires access to computing. So, moving forward. So if I look at what's involved here, this is looking at a digital twin. It combines a lot of high compute need elements. There's the real-time analysis, and if you're using ML for that, you need to train it. You have to teach it how to do that analysis first. You need to run that analysis, then you need simulations, you need a surrogate model, you need to train that, you need rapid retraining to adapt to these experiment decisions, and you need decision-making engines. So all of these things need to work in tandem, all at the same time, within the same time scale, which is of order minutes to hours, really, and some things even in seconds, in order to run an experiment. So the computing, the high-performance computing, the edge computing, have now become intimately coupled to the experiment. They are now part of the experiment. Another way we'll use HPC is to connect scientific instruments to the remote site in order to do the training. One example of this is some of our peak finding and classification, some of these networks. The model that we built, it was too big to train on SLAC's shared science data facility. There weren't enough resources to do that efficiently. We had a lot of data, and we needed a very large model to capture the complexity and variations within that data. So we had to look to Oak Ridge, who provided us with an allocation that allowed us to do that. Along the way, we also investigated how to stream data from LCLS into Oak Ridge. And what we did is we pre-processed some of that data locally on the S3DF, and we sent only the products that were useful, AI-ready data, let's say, over to Oak Ridge for training, and then got the weights back. So that's a way of doing that. And these one-to-one, we have these one-to-one collaborations with NERSC, with Oak Ridge, with Argonne, and what we need to do is we need to turn those into a many-to-one, so many light sources to one of the leadership class facilities, and many-to-many. So many light sources to many leadership class facilities. Another example is Argonne. So we've connected there to retrain our models. All of this is in the goal of creating smarter instruments. We develop the models offline and move them to the edge, and we have to retrain on the fly to adapt. And Argonne has a data center AI that rapidly allows us to rapidly retrain our model and bring the model weights back and then apply them at the edge. And so we can adapt to within half an hour to an hour, maybe even faster, to dynamic conditions at the experiment. But again, this requires streaming data, raw data, now out to Argonne, interpreting it, analyzing it, retraining, and then sending something back. These interconnected loops are everywhere. So what else is coming down the line? The high-performance data facility is something that the DOE is building. It's going to facilitate scientific data as an asset. It should be said that our data is a national resource. It should be treated as such. The light sources, these DOE facilities are producing mountains of data, be very valuable for training, for AI in the future, but we need to make it AI ready and put metadata on it and organize it in a way that we can use it effectively in the future. The integrated research infrastructure is an initiative that will combine these leadership class facilities and allow that seamless access to computing that we need for those cases where it's necessary to do the things that we don't have the capacity to do locally. SLAC and LCLS have kind of been heavily involved in this. We've been using these leadership class facilities quite a lot for a large number of projects across a wide number of facilities and wide range of projects that involve both experimental and observational facilities. So how does this kind of map on the need space? So there are still lots of computational tools and capabilities that need to be created. And the HPDF and IRI will provide some of that infrastructure that's needed in order to do machine learning, but we still need to create scalable libraries. We need to be able to run these things. We need to build models. We need to fix these last mile problems, these policy questions that make it higher touch to go to a remote facility than it is to remain in my own facility. We need better workflow and orchestration tools. I described some very complicated scenarios where there's a lot happening, and we need to be able to contain that and manage that in a way that doesn't require a human being to hand tool it every single time a new experiment comes in, because we have hundreds of experiments per year that we have to serve. So SLAC is approaching this with 3 pillars. We are trying to do intelligent data extraction at the edge. So this is trying to push the smarts into the instrument itself so that we're producing actionable information that we can react to and AI-ready data. We are trying to do experiment steering using that information that's generated by our smart detectors, our smart instruments, use that to steer steer the experiment so we can take the data we want, only the data we want, and make sure that it's of good quality so that the user goes home with science information, not raw data. And then on the computing side, there's the massive scale data analytics that we need to do. There are lots of opportunities here with the HPDF and IRI coming on the scene, using those effectively, jumping onto that moving train and making sure that our hundreds to thousands of users per year, can actually use those facilities without running into roadblocks will be a very important thing to address as we go forward. All right, so I will conclude here, and I'd say that HPC creates opportunities to rapidly convert data into science. Again, our data is a national resource. This is the information, our currency, what we produce that is of value to basic energy sciences, and it underpins much of the technology that HPC cares about. These are the way we make better microelectronics, higher density things, lower power computing. So the DOE facilities can drive this new era of both data generation and combine it with AI-based analysis for science through the use of computing, edge data processing, and computer science research. And it requires smarter work on all 3 of those and putting it together in a way to optimize these data pipelines, these changeable, beautiful, variable, dynamic data pipelines to do this breadth of science that we're doing at the experimental facilities. And what that involves, edge to exascale, it's building smart AI-enabled experimental facilities, connect them to leadership class facilities. It means doing more with less data. I didn't say too much about this, but data on the wire is raw data is very ugly in a way. It's got dropouts, it's got detector malfunctions, it has some great stuff, and then it has some where there's no shot, no information at all. And sorting through all of that at 1 million frames per second is no longer a human enterprise. A human being is not going to, we basically went from an era where you handed scientists a USB stick and say, have fun with MATLAB on your laptop, to handing the same user the keys to a high-performance computer and saying, best of luck. We need to bridge that gap, and we need to work as smart as we can to connect to this leadership class facility in a way that the scientists can use it responsibly to get the answers they need. So doing more with less data here is really all data are equal, but some data are more equal than others. So sort that data out early, tag it, curate it, and make sure that what gets produced and what comes out is AI ready so that we can evolve our algorithms. It's not enough to just train a model and then expect to use it for 2 decades. That's not going to fly. We need to build things that evolve as a function of time. We need to use actionable information produced by our detectors, our instruments, and use that to seize the means of data production, use it to drive the experiments to take the data we want, and then finally treat our data as a national resource, because it will feed this AI innovation. As previous speaker noted, there's the quote from Feynman that says that your theory can be, paraphrase here, theory can be as lovely as you want. If it doesn't agree with experiment, it's wrong. And so the experimental facilities are the test bed, the place, the proving ground for all that theory. And we need to merge that with the latest AI/ML tools and high-performance computing to really accelerate scientific discovery in the coming era. So I will end there and pause for questions. I'll leave you.
Thank you, Jana, for the great presentation. If there are any questions, there are microphones at these aisles, so please line up there. So maybe we'll start here.
Yeah, thank you, great talk. I have 2 questions, actually. The one question is, how do you handle the software development and the maintenance of code over, you mentioned 10 years of keeping the data. And how do you handle the what's it called, the conflict between running classical HPC simulation and running MLOps for AI training and all stuff? How do you handle that internally?
So the first question is, how are we going to handle the maintenance of the software? It is an issue. I don't know that the techniques that we've used in the past are going to be the most effective ones going forward, because they tend to be the sort of things where a user, a postdoc, or a scientist that operates at the facility has built a package, turns out to have some usefulness, other people take on, other people start using it, contributing to it, it becomes an active space on GitHub, people add, there are pull requests, and then at some point, that person might go off into industry or take a new job somewhere, and the curator for that software is now gone. So we have to make sure that there are tools to do the knowledge transfer and documentation, and that we can maintain things. I think the user facilities themselves have a role to play here, because we are stable, we are connected to that facility and use those tools. So if a piece of code is determined to have value beyond the life of that postdoc and that particular experiment, then we need to develop the means to maintain that code and give it longevity. I don't know that we have a really great roadmap for doing that yet, but it's certainly a recognized and known and understood problem. So there's that. And the second question, remind me again, was the HPC, right?
Yeah, it was about the different
contention between simulations and these high-rate, bursty sorts of algorithms, and how do you, at the moment, so we are working, I can't speak for the high-performance compute facilities that are out there. They will have their own means of dealing with this, but they know about the problem. So we will work with them to say, this is the allocation we need. They will make sure that reservation is available. In the end, it should make things more efficient, because by taking the data we want and doing some pre-processing on it, maybe we're going to present them with something that's less of a computing challenge, I don't know. But you're right, there will be some tension between the simulation jobs and the high-performance jobs, and how we handle that, whether we preempt or whether we just allocate I don't know. I think it is a good question.
Maybe we'll take this question here.
Think this one. Oh, there we go. Hi, thanks so much for your talk. I just had some questions about the details of your data reduction pipeline. For your streaming technology, are you doing directly from the sensor over to the leadership class facility, or do you have a Kafka or some sort of streaming cluster online that assists in that transfer? And related is just for those models, how do you make sure you have all the software dependencies met at both sides, at both facilities?
Yeah, so the data reduction pipeline is a SLAC invention, and it is rather specific to our data system, the LCLS data system. It's a compute layer that consists of CPU, GPU, FPGA, and whatever accelerator we decide to throw in there. And it is all built by us, and it's closely coupled to the experiments and the experiment techniques that we expect to see. So we've worked very closely with the beamline scientists to identify what form of data reduction can you do that will not harm the experiment. And in the first generation, I should say, it's a first do no harm philosophy. We need to earn their trust. Understand that these facilities are such that in the past, we've written out raw data, and the users go home with raw data in all its glory. And now we, the facility, are inserting ourselves into that path and claiming to do some operation on that data before it gets handed to the user, before it gets written to disk. And that's a daunting proposition. So what we've done is we've basically asked the scientists, what's the first thing you do when you run offline? And they say, oh, we get rid of the junk. Great, tell me what that junk is. And it turns out there are roughly 10 common ways of reducing that. You throw out the stuff that doesn't have a hit. You do lossy or lossless compression on it. And we use SZ compression out of Argonne. That slide didn't make it into this version of the talk, but we have a very strong collaboration with Argonne to do lossy compression with error bounds for the places where we can't just throw out things. And we do feature extraction, so we do peak finding and things like that. And we are building trust with our users to make sure that their traditional algorithm and the high-powered AI algorithm will agree. We do careful validation to ensure that we are not introducing some bias into the data set.
Okay. And we'll take one last question here from the middle.
Thank you so much for your talk. So in more traditional science thought, very disciplined design of experiments will ensure that you're getting the appropriate sampling during your experiment. Can you compare and contrast that traditional thought to using AI recommended, suggested, real-time changes to your experiment design and what some of the costs might be of moving away from pre-planned experimentation?
Yeah, so that's a can of worms. That's difficult to unpack. So yeah, AI has a lot of promise in suggesting what to do next. The way we're using it at the moment is a quite simple way, in a limited sense of, tell me where to sample the time point, or tell me what magnetic field to apply, or, it's asking a very simple question with a very simple point of control. But as AI use grows, that can become quite larger, more sophisticated. And what I think we lose right now, there's a lot of human intuition involved in how to exactly get the experiment to do what you want. And I should say that our experiments at LCLS tend to be the Wild West of experiments. They're very dynamic. Things change in the middle of the night. You add detectors because you want a diagnostic somewhere that wasn't there before. How do you prepare for that? You have an AI that's trained to do a specific thing, and now you've just added a diagnostic that didn't exist before. So, we need to somehow translate a lot of that human intuition that goes into the experiment and give it to the machine to do the hand tuning bits. The bits that don't require too much of a human being, right? Like, there's a lot of things like beamline alignment that are multidimensional, phase-space, difficult things to do. Human beings currently do that by dividing and conquering. I'll do these two parameters first, then I'll do these two parameters, and then I'll do this, and then ultimately I'll land on a target. Machine thinks about it quite differently. And when you compare a human to a machine performance, like, the machine doesn't do as good as the best human, but on average it does okay, and it goes a lot faster. So it provides consistency. At the moment, we're using things in a way where the answer is obvious. Like, if I get the wrong answer and I've shot the beam over here instead of over here, like, that's obvious. What happens when we start using it to do science? How do we know that it's right? And that I don't have a great answer to, because it's an untried space. We can only use simulations and data, canned data in previous experiments to sort of compare and understand and validate the performance of our algorithms. And then do our best as we march into the future. But yeah, you want to be very careful not to introduce misinformation into the scientific domain and base future papers on something that has a false conclusion. So it's a warning sign for sure, and I think the only thing you can do is validation and verification and uncertainty quantification, and then use that combined with human intuition.
Well, thank you again, Jana, for that wonderful presentation.